Okay, hi everyone. So this is my video overview for MBAI5310G, assignment 1 and question 2, which is using the auto MPG dataset from UC Irvine. So to start, MPG stands for miles per gallon. So I started by downloading the dataset from UC Irvine using the provided link, and then I loaded in pandas to read the file. And since the raw data didn't include a header row, we have to define a list of names for the columns before loading the dataset into a, which would be this area here. So I added all the column names that corresponded with the data, which included MPG, cylinders, displacement, horsepower, weight, acceleration, model year, origin, and car name. But since this file did not use commas as a separator, when I initially tried reading it using the read CSV method in pandas, it didn't work. So I did use Gemini AI here to help me figure out where I went wrong, and it helped me realize that this data set uses white space to separate the values. So we use assign the columns and NA values to treat question marks as a missing data. So here we added in the separator and the NA values here to properly read in the file, and it loaded in correctly, and it helped us create this data frame named auto. So then in the first part of this assignment was to drop the car name and origin attributes. Use the dot drop method in pandas to remove the car name and origin columns, which I reference from the pandas documentation for the setup. So from here, we use print auto head just to check that the columns were removed. So we can see that there's MPG, cylinders, displacement, horsepower, weight, acceleration, and model year, and no more origin or car name. So moving into the second part, which is part B, which is to attribute horsepower. The attribute horsepower has 6 missing values. Fill these up with the average horsepower for the respective number of cylinders. So we would identify the missing values and fill the space in with the average horsepower for the amount of cylinders of each car. So for this part, I referenced the pandas documentation and found the .to numeric method that would help in forcing the horsepower column to become numerical values, since previously it was all text or strings or missing. So this line reviews the horsepower column and changes any text to NAN, which is not a number. And then the next part, we use the fill NAN values and the dot transform to fill the not a numbers with the average of horsepowers for each group of cylinders. So that is this part here, which is the dot fill NA and the dot transform. So this last line calculates the average horsepower for each group of cylinders. So this would be cylinders of 4, 6, 8, and etc. And we use those averages to fill in the missing values for the same groups. So this works better than the typical dot mean method, which would have just averaged all horsepower regardless of the cylinder group, which would skew the results a little bit. So using the dot transform of the mean, it allows us to average all of the horsepowers for cars that have cylinders of 4, cars that have cylinders of 6, and etc. And it would help us fill in more accurately the missing values. So this last line, I also use AI just to help me check if the previous lines got all of the missing values. And we can see here that there are 0 missing values remaining. So we can move on to part C, which is to edit the model year column, which previously had only 2 digits for each row and the last 2 numbers of a year. So it was all in the 1900s, so it had years for like 70, 71, and 72, and we want them to read as 1970 or 1971. So we can change this by simply adding 1900 to each value to make it 4 digits, and then check that the changes went through using the print function. So we can see here that the model years now all say 1970 and as it goes farther down as well. So we're able to move into the next part, which is part D, splitting the data into 50% training and 50% validation sets. I loaded in all the necessary libraries, and we started by splitting it into auto X and auto Y, where X was all of the inputs excluding MPG, and Y was the target value of MPG, since this is what the model is learning to predict. So here we dropped MPG from the rest of the features, and here we only selected MPG. So then this line then splits the data into 50-50 into training and validation sets, where the training half is used to learn and train the model, and the last half is for the test and validation of the model to see if it learned anything. So here we split it by 50%. And then we also moved into scaling the data. So before we can create the model, we use the standard scale. This part adjusts all the numbers to be on a similar scale. So since there are columns for quite a few different things, such as weight and then number of cylinders, for example, this prevents the high numbers from being treated more importantly than smaller numbers, like comparing 4,000 pounds to 4 cylinders. So this part I also reference from Jaron Chapter 2, Feature Scaling and Transformation, and Chapter 10, Implementing MLPs with Keras. So after scaling, we can see the result here. We also printed out a few lines just to double check that everything is working correctly. So we can see here the 50-50 split of 199 for each set, and we can move on to training a model. So in this one, we created and trained a model to predict the MPG of vehicles. To start, we initialized the model through here, and we added the 6 input features as the shape. And then we added 2 layers with 64 neurons each and used the ReLU activation to allow the model to learn the changes in data. And then the last input layer or last output layer has only 1 neuron with no activation, since we want the model to output just one singular number, the estimated MPG. So then we set the compiling and learning rules using Atom as the optimizer, mean squared error to calculate the penalty for wrong guesses, and mean absolute error to track how many MPGs off the model is. So we also use history here and started training the model using 100 epochs, and it kept a log of the process. So we can see as it runs here. Okay, so we can see that the model has reached 100 epochs. And now we can move into part F, where we're going to use the model we created and add in some new cars to see what the model will predict their MPGs to be. So we created 10 new vehicles based off of the assignment provided, and we added in all 6 categories of information for each vehicle. And then we used the .predict method to generate its best guess for their MPG. So I also used AI here to help create a print line to help us review the results just a bit easier as the model loops through and then prints out its final predictions of estimated MPGs. So we can run this code here, and we can see the estimations for each car. For example, car 1 was estimated MPG of 127.62, and car 10 had an estimated of 99.54. So after seeing the results, it seems the model's predictions were calculated strongly using the horsepower and time relationship. Since the original dataset was using car models from the 1900s, it assumed that as time passed, the models would improve their MPGs. So in some of the new cars that we entered, the model year was 2025, and it assumed the models got more and more efficient. So by the time 2025 came around, it assumed that fuel efficiency had improved a lot after 40 years. And it also seemed to use weight as a strong influence. It assumed that lighter cars are more improved than heavier cars. It understood it as that cars that are heavier take more energy to move than a car that is much lighter, so that when the weight increases, the predicted MPG must drop. So overall, it seems the model captured a few patterns and assumed that the lighter and newer the car, the more fuel efficient it is.